Understanding Heat Transfer Methods in Aluminum Fenestration Systems. Welcome to Building Knowledge 101. In this video, we share information about the three methods of heat transfer: conduction, convection, and radiation. The first one was heat transfer. There are three methods of heat transfer. The first one I want to talk about is conduction. Conduction is heat transferring through a solid material. It's the interaction of the molecules in a solid material that allows heat to move through that material from one side to the other. The next is convection, where conduction is in a solid environment, convection is in a fluid environment. So air or water turnover. So you've got circulation of molecules in a fluid environment where they move from a warm side to a cold side. Heat is always going to move from the warm surface to the cold surface, warm side to another. So convection is in a fluid environment. Then radiation is heat being radiated from one surface to another. If you put two surfaces juxtaposed to each other, heat is going to move from the warmer to the colder through radiation. So it's transfer of heat through radiation or electromagnetic waves. Here's an illustration of what we mean by conduction. You can see this is a section of an aluminum window frame, and it's sitting on a very cold frosted surface. And you can see that the lower half of the frame frost has easily traveled up the aluminum frame to where it hits a thermal break. That's a pour-in bridge thermal break. And what we've done there is we've introduced a low conductive material into the aluminum, and we've broken the path of heat or cold, in this case, moving through the frame from one side to another. The low conductive material there stops the path and prevents the heat or cold transfer from continuing all the way through the aluminum. So your thermal break in a commercial frame is going to separate the exterior metal from the interior metal. So there's not a direct path for temperature to transfer back and forth between the two surfaces of the frame. Now, convection I described as being in a more fluid environment. So if we take a look at this section cut, this is a storefront vertical frame. You're going to have a cold surface to the exterior on the left and a warm surface on the interior to the right. And you notice it's a hollow chamber. So it's a hollow extrusion, frame shape there. So you're going to have cold on one side, warm on the other. And as air circulates, you're going to have heat transferring through that tubular shape from the warm side to the cold side. So if you look at this window section, here's a nice illustration of window section. Notice how here, instead of being one open hollow, they're chambers. So the frame is divided into chambers. This prevents you from having one warm side and one cold side. So that's going to cut down on convection. You can see in this illustration here, these chambers now, air would circulate within them, but you don't have a complete cavity where air is going to move from one side to the other, allowing heat transfer through convection. And then as far as radiation, here's a nice photograph of a dormitory, and you can see all the windows. So great use of windows there for daylighting and views. But if you notice, the blinds or the shades all appear to be closed. And this is a morning photograph, so most likely we're getting direct sunlight through these windows. That's bringing heat in, and the occupants on the other side have closed their blinds to cut down on the heat coming through. So this glass probably does not have a low E coating on it. So let me explain what that is quickly. Emissivity is a measure of a material's ability to radiate temperature. The higher the emissivity rating, the more efficient the material is at radiating heat. So something that has a low E, a low emissivity, is going to be inefficient at transferring heat. It's going to reflect heat away instead of radiating it through. So the goal of low E coatings on glass is to reflect heat back out. So you don't have an application like this where blinds are having to be used on the interior to stop heat coming through. We refer to what's called the RAT equation, R-A-T. When we're looking at insulated glass units, sunlight hitting it or solar heat hitting it, three things are going to occur. One, it's either going to be reflected away, it's going to be absorbed, or it's going to be transmitted to the interior. So that's the RAT equation, because solar energy is either going to reflect away, be absorbed, or transmitted to the interior. The goal with low E is to reflect the heat away and prevent it from moving to the interior. Interior thermal comfort. If you look at this upper photograph, this is a facility in northern Midwest United States. So it's in a cold area. There's snow during the winter on the exterior of this facility. And if you notice, it's got a nice comfortable seating group right in the corner there with glazing on both sides of it. If this was a non-thermal frame, you would not be able to use that seating group during the winter. It would be too uncomfortable. You would have a cold area around that exterior glazing where heat was being pulled through, and cold on the inside would be considerably colder. So it wouldn't be comfortable sitting there. Then if you look at the picture in the lower left, this is a college library. We've got a nice curtain wall there on the left side. If you look on the floor, you can see the shadow of the curtain wall. So sunlight is coming directly through the glass there to the interior. If that glass didn't have a low E coating, it would be incredibly hot on the interior. You can see there's one person sitting in a chair, comfortably studying. So the glass is being used to reflect heat back out, creating a nice thermal, comfortable area on the inside. And then the pedestrian walk area in that third photograph on the right, you can see direct light coming in. If that didn't have low E coatings on it, that area, that corridor would be extremely hot. So again, interior thermal comfort is very important, because without it, you're losing usable floor space around the perimeter of a building because it's uncomfortable being around it, either very, very hot from direct sunlight or cold from heat being lost through your frames if you're don't have a proper strategy for handling the temperature change. So when we look at how frames perform, the AMA 507 test calls out having a test chamber where you've got 0 degrees represented by the dark in the scale on the right on one side, 0 degrees on one side, 70 degrees on the other side. And when the frames are put into the test chamber, the heat flow through the elevation is measured. So here's an example of a non-thermal frame. And if you notice now, the glass in it is an insulated glass unit, so you're maintaining a warmer surface here, represented by the brighter green that you can see in the scale here. Warmer surface on the inside, and then cold on the outside, represented by the dark gray in this range. So the insulated glass unit is performing very well. But when we look at the frame section here, the interior is showing considerably colder than the glass. It is a blue in this range, so this is colder here. Notice that the exterior of the frame is this purplish color, which is warmer than the dark gray in the insulated glass unit here. So in this application, temperature is being pulled through the frame. So we're losing a lot of heat through this area. We're warming up the outside of the frames, and this is cooling down. So heat is being pulled through to the exterior. But this example now is a thermally broken frame. If you notice here, the interior aluminum is staying warmer like your insulated glass unit. They're working together as a system to protect the interior and keep the heat on the inside. Now the exterior of our frame is this darker gray that you see representing here, closer to the outside temperature, and the interior is a lighter green, so we're maintaining warmer. So this is what your thermal break is doing. The non-conductive material introduced right here is interrupting the flow of heat through the frames. This example, there's no thermal break in here, so heat is flowing very easily right through the frames. And in this example, with a thermal break, we're stopping the flow of heat at this point and creating a thermal system combination between the glass and the frames. That is all we have time for in this video. If you'd like to watch more of our 101 video series, subscribe to our YouTube channel, Kawneer Company, Inc.